So now that we've covered the theory of radiated emissions and how electromagnetic waves originate and propagate through space, wouldn't it be nice to actually see them and measure them? So this is what this video is going to be about, as I will use a spectrum analyzer and show you my typical setup for measuring radiated emissions. Of course, in the real world, you would want to go to an anechoic chamber to get your measurements precise and measured against specific standards that we mentioned, that the most notably CISPR 32 as well as FCC Part 1547. Those standards set the limits for radiated emissions and also tell you exactly how to measure them inside anechoic chambers. But of course, I'm not inside an anechoic chamber right now. Instead, I'm sitting in an average office environment, so it's not going to be possible for me to accurately measure the performance of my device in a far field. So what I'm going to do instead is I'm going to use my near field probes and measure the performance of my device in a near field. And to do that, I have a choice of electric field and magnetic field near probes. So I have 3 near field probes here. So this is your typical loop antenna that we use for near field measurements of magnetic field. The other probes are electric field, and this one is a broadband electric field probe, where this one is a narrowband electric field probe. So the difference between them is that you would use this probe to kind of locate approximate area of the emission, and then you would use this probe to locate the precise area of the emission. So how exactly you using those tools really depends on the problem that you have. Whereas in this situation, I don't actually have a problem. I'm just going to show you my setup. But really, you should be starting with a problem. So if you know that you have an emission at a particular frequency, then you would use those tools to locate this emission and find its source. But today, we're just going to look first at the performance of USB cables and the sort of emissions that can happen when you don't use an adequate shielding inside a USB cable. And secondly, we can look at the printed circuit board analysis and see what the performance in near field is with magnetic and electric field probes. But before we get to it, let me first talk a little bit about the spectrum analyzer that I'm using. And this one is the Rohde & Schwarz FSC6 spectromizer that can measure between 9 kHz and 6 GHz. It's a very wide frequency range for such a small and portable box, and this is why I'm using this spectrum analyzer. It allows me to easily transport it from one location to another. Even though this is an entry-level spectrum analyzer, so it doesn't have quite a lot of features that you would get with an expensive one. However, the more expensive spectrum analyzer is, the less likely you would be to carry it, let's say, in a trunk of your car. So instead, it's best suited for an anechoic chamber where it's stationed permanently. This spectrum analyzer here I would probably not recommend for anechoic chamber setup because, again, the amount of functionality inside is quite limited compared to the more expensive versions. So now let's have a look at the typical setup of a spectrum analyzer and how would you need to set it up for accurate measurement. So I have plugged in my audio interface and I'm now playing some music. So that means we are ready to actually measure the communication over the USB cable. You don't want to measure it if there's nothing playing, because obviously that means it's dead and not doing anything. So the first time you turn it on, it's going to start with a window that looks something like that. Now obviously this isn't very useful, or nor does it contain any information really. So let's go over the buttons that you get. You have a frequency button, a span button, an amplitude, bandwidth, sweep, measure, trace, lines, marker, and such. So obviously the different spectrum analyzer will have slightly different options. However, the majority of functionality is the same. So the most important things you need to pay attention to, well, first of all, is frequency. So as we will be looking probably at much lower frequencies than 6 gigahertz, I'm going to set it to start at 200 megahertz and stop at 800 megahertz. Now bear in mind the range of those probes is from 9 kilohertz to 5 gigahertz, so I could have used it for a much wider range, but this is just giving us a very large window that doesn't contain a lot of useful information. When we narrow it down to a specific section, we can see a lot more. Now obviously, as I said before, it really matters what are you doing and what sort of problem you've got. If you already know that you're failing at a specific frequency, then you're obviously going to set the frequency range with a center frequency at the frequency that you're failing at. So the next window that you really need to look at is the amplitude window. And your reference level actually has a very important impact on the spectrum analyzer, as it sets the maximum level you are expecting from your input device. Now for a near field probe, it probably doesn't matter as such, so I'm going to set it to 30. And in this window we can also enable a preamplifier that is built into the spectrum analyzer. However, you must purchase a subscription of some kind to enable that. And if your spectrum analyzer does not have a preamplifier, otherwise it's called low noise amplifier sometimes, you really need that to make accurate measurements. So you can either design your own or you can buy it off shelf from a third-party company. And typically you want about 25 to 35 decibel of gain. Obviously the selection of frequency for your low noise amplifier must match the frequency of your spectrum analyzer. So let's enable the preamplifier, and we can see that the noise floor immediately dropped, which is a good sign. The next window we want to look at is the bandwidth, and we got two types of bandwidth in spectrum analyzers. We've got resolution bandwidth and we've got video bandwidth. So the resolution bandwidth is setting up the eyes of the spectrum analyzer, or the window through which it's looking at the peaks that it's measuring. So if you have a very wide window, then it's not going to distinguish between various peaks easily. So you want to start with a wide window if you're looking at a wide frequency range, and then you want to narrow it down. As you reduce your frequency, you also want to reduce your bandwidth. So I already reduced my frequency to about 400 megahertz span. So now I'm just going to reduce my resolution bandwidth as well to about 100 kilohertz. And this is where I may want to adjust my reference level so it stays somewhere in the middle of the screen. As for the video bandwidth, I suggest you just follow the same value as you set for resolution bandwidth. However, you could play a little bit with it, and it's not going to change things too much now. It's just going to define the resolution of the noise floor. So we could set it a little bit higher or lower than resolution bandwidth, but like I said, I tended to leave it the same. So a related concept is a sweep time of a spectrum analyzer, because it actually depends on your resolution bandwidth. Whereas I adjust resolution bandwidth rather than sweep time, but you could do it other way around. And the sweep time is basically the time it takes to make a measurement. So in this setup, the sweep time is set to automatic and a continuous sweep. So that's the other thing you could do. If you were looking for a one-off clock signal, you could just make a single sweep rather than a continuous sweep. Right. So then the other things we want to talk about is traces, and you have different modes of traces. So you can either have a clear write trace that is constantly refreshing itself, or you can set it to average, where it averages across several counts. And obviously, the more counts you set to average to, then the longer it's going to take to complete its averaging. So I tend to set it to about 30 counts, and pretty much at this point, we are ready to begin our measurements. As you can see now, we have significantly simplified what we're looking at compared to what we began with. And this is being the noise floor of the spectrum analyzer. We can save that and basically save it to memory. So now, when I'm going to perform other measurements, I will see the background as the memory, and this is going to show me the noise floor of the spectrum analyzer itself without anything plugged in. So now let's connect the probe, and I'm going to use this BNC cable with an RF adapter so that it plugs in here, and the other end of the BNC cable plugs into the near field probe like so. So as you can see, immediately the noise floor of the trace 1 is starting to rise. So we are now having some ambient spikes that we just probably perceiving from LTE or some other spurious emissions. You would always have them in your system unless you are in anechoic chamber. So this is kind of why we tend to go to an anechoic chamber. We can locate the peak by selecting a marker and basically add it to the spike that we want to see. So for example, I noted this spike here. So I'm going to put a marker there, and I can see that this spike is at around 391 megahertz. So depending on how I move my near field probe, I can see it's going up or down. And then you can add another marker, and you also have what's called delta frequency measurement. So in this particular spectrum analyzer, it defaults to delta when you add a new marker. And the delta is basically telling you the distance between the peak that you previously had on your marker 1 and the marker that you just added. This is a very useful feature when you want to measure or find the clock frequency, because if you seeing multiple rasters, so for example coming off a power supply, so like harmonics, then you can see the distance between those spikes, and this distance is typically going to be the center clock frequency of this DC-DC converter. So for example, here we can actually ironically see some of those rasters. So now we are kind of ready to actually analyze this connection, and with a magnetic field probe we can just scan the cable, and we can see that as I move it at different positions, it's changing. What I could do as well, I could go back to trace and set it to max hold. So as I'm scanning this cable, I can see where the noise is at its maximum. And really, when I'm doing this kind of analysis, I'm just looking for gaps in the shield, because cables are very often terminated with some sort of a pigtail rather than 360 degrees connection. So this is sort of thing I'm looking for, and I'm looking for like very bad performance, but I'm not really seeing that. So it seems that this cable is actually quite good. So while keeping the span the same, we can look at different frequency ranges. So for example, let's just set the center frequency to 1 gigahertz. And now we're getting a lot of LTE in the room. So this is what you would expect at around 700 megahertz. So that tells us this is around 592 megahertz, which is one of the typical LTE bands. Again, this is kind of why you want to go into an anechoic chamber to do accurate measurements, because inevitably you will get very high spikes from the environment. But ignoring that, we can set the frequency again to something less, say 800 megahertz. And we can see that overall the cable doesn't really have much impact on the performance. So that means that the shield inside this cable is quite good. Yeah. As I lower the frequency, I can now see some of the emissions that look like DC-DC power supplies coming from inside this unit. This is normal because that just means that it's working as long as they're below the limit in a far field. You can also, by doing that, watch out for the breaks in the shield. So now you can see a very clear kind of pattern here. So I can see that in this position here, as I go over the knob, it's quite consistent. And the other thing we can do is we can set the frequency to very narrow one. So let's say start at 100 megahertz and end at 120 megahertz. So here I actually managed to find some power supply rasters in this region here. As you can see, there is a hole that is a direct input for a guitar, and there is a hole for metalwork. So that means that frequencies can actually, and electromagnetic waves can pass through it. So as you can see, we get those rasters, and if we set, so we can now set the trace to view, and that was a bit tricky holding the camera at the same time. So we can now add another marker, and this is telling us the kind of frequency between those two. So let's move that one a bit, and now we can see that. So you can see clearly that the frequency between them is 1.3 megahertz, and this is likely to be the center frequency of this DC converter that you have inside this device. So the Rode & Schwarz has an instrument view kind of app that allows you to basically bring those kind of traces into your computer. So as you can see, this now gives me all the information that I have seen on this window here, and I can analyze it independently with a bit of, so I can here I should be able to zoom in on those spikes, and you can do everything that you can do on the spectrum analyzer on the computer, except that it's not real time. So unfortunately, if I wanted to edit it at the same time and have a real-time data capture, it is not possible with this model. Also, as I already outlined, but it's worth highlighting, to detect those kind of power supply rasters, so you really need to narrow down the frequency range you're scanning so that you're not looking for more than 20 megahertz bandwidth or so. Otherwise, you're just not gonna detect those spikes. It is also much easier to detect them at lower frequencies rather than on higher frequencies. But what tends to happen with DC-DC supplies and their rasters is that they are quite continuous throughout the entire range of frequencies, so they can start from 1 megahertz and go up to 1 gigahertz quite easily. So you will see those rasters there and then all the time. So now let's have a look at this board that I brought with me, and that is simply powered with a USB cable. I'm not sure why it stops playing. So you can now see the board is actually powered up, and all it is a Telit modem on a base hat PCB. I do not have a SIM card for it, so we're not going to look at its LTE, maybe next time. But for now we can just analyze at least what the near-field performance of the circuitry on this board is like. So first of all, let me reset what I've been looking at, so that let's reset it back to some default values, so like start at 100 megahertz and stop at say 600 megahertz, and trace back to clear view. You don't want to see that. No, we need to exit view. Right. Sorry. Average. Okay. So we're back on our default screen with this near-field probe, which is still the magnetic near-field probe that I've been using. I'm not completely sure why I'm receiving some spike here, but let's just delete all one and new marker. And so that's a spike at 217 megahertz. That seems to be caused by the environment here. So this is just something we need to note, and we can do that by saving that as a trace memory. So now we can look at the actual board. And just when we using magnetic field probes, it really is important as well in what orientation they are, because they are polarization sensitive. Which means that as the electromagnetic wave originates from the printed circuit board, it's going to have either magnetic or electric field dominating in the near field. So you want to try both polarizations so that you get an accurate picture. So far it's pretty good. I'm not really detecting any kind of noticeable spikes, other than maybe in the lower ranges, which is basically where my USB cables are. So I can play a little bit with frequency ranges again, just to have a little scan and look like if there is anything changes. So So we can see that at low frequency ranges is a little bit more exciting than at high frequency ranges where we know. So here, I said 800 megahertz, we've got mostly just our LTE stuff and nothing else. And like, if I were to go to say, let's go to, let's say 2.5 gigahertz or something, and this is our Wi-Fi which is running in this building. So but it's actually pretty quiet, which I'm a bit amused, because I would expect a bit more of it everywhere. So as you can see, analyzing this board at this frequency is probably not going to be very informative. So let's go back to the low frequencies, and I saw that at about 80 to 160 maybe we saw some spikes. So this is what we can actually concentrate on. So again, we can add a marker. And this is kind of giving us some sort of idea of what we're dealing with. We've got spikes at 90. It's all kind of usual. Nothing really that looks like it's going to fail an EMC test. And you can see now the distance between those two spikes is 20 megahertz. So what we can do now is we can change our probe. Rather than using magnetic field probe, we can use an electric field probe, and let's see what happens actually. So I'm going to begin with a broadband electric field probe, and then we will switch to the narrowband electric field probe. So this is the broadband electric field probe, and now this type of probe is polarization insensitive, which means it doesn't matter in what orientation you're looking at it. It's gonna give you pretty much the same response. So what I'm trying to do is I'm trying to find the area where those spikes are at the highest level. That seems to be around here, which seems like we've got a voltage regulator here. And again, if I just stop this trace, I can figure out the frequency of the center frequency of this converter. Yeah. But before we do that, let's switch the probe again. So now I use this broadband probe to identify the area that is of interest. And now I'm just going to narrow it down even more. So now I'm going to switch to this near field probe that looks like just a pencil, and it's quite pointy, which is really interesting to see what that's gonna look like. So I know exactly where to point it now. So I'm gonna go straight for it. Right, and you can see that. So you can see that it's changing quite a lot just as I'm moving it 1 millimeter away from this area. And this type of probe can be very useful for identifying ground plane breaks, whereas you can just go along the trace and find where the trace is got broken plane underneath it. So now I switch to the view, so now this isn't changing. And I can actually play with my markers again. So, for example, we can estimate the distance between those two spikes. And we can see that they are around 2.2 megahertz. Yeah. So this PCB actually has a schematic in the internet, and we can see that the regulator I was looking for is TPS 62086. So let's have a look at the center frequency of that. TPS 6. So this is a step down regulator, and I identified it on a PCB. And you can, here we go. So PWM switching frequency is 2.4 megahertz, which is, well, not exactly the value that we measured here, but I say it's close enough. So as you can see, that's pretty much what we have predicted, even though it's not quite the exact value, but it's close enough. And there is some uncertainty when it comes to measurement with spectrum analyzers. I can now get this new trace I was just looking at, and this is now allowing me to capture it on a big screen, so I can see those center spikes, so I can see quite precisely where the center frequency of that spike is. So again, a resolution like this wouldn't be possible with wide bandwidth. So you really, this is kind of the drill. So we start with wide bandwidth, and then we narrow it down, and then we get some accurate readings with near field probes. So this is pretty much everything I wanted to cover in this video, which is talking about your average near field measurement setup. And like I said before, it all depends on what kind of problem you have at hand. And based on that, you're gonna decide what sort of measurements you're going to perform, and whether or not you even need to do that. Because if you pass EMC, then you don't need to do any of this. But unfortunately, or fortunately for me, because it keeps me employed, most products don't pass EMC first time. So this is why we need this equipment, and this is why we need this setup. Going out to anechoic chambers and test facilities such as Intertech or UL is always a very significant cost to the business. So you really want to minimize the amount of times you do that. Then the typical procedure becomes that you first start with your home setup, and you just see that everything is good and there doesn't seem to be any outstanding issues. And based on what I've seen today, I am quite confident that this board with this USB cable is not going to cause me any issues. So then I can take this setup and go to the anechoic chamber where someone else will be doing the testing, because I don't work there, and they will be following the regulations and the standards quite precisely, which I don't necessarily have a great deal of knowledge of the test setups and all the details of EMC testing. And then after the testing is complete, you obviously get the result, and that tells you whether or not you need to go back to the lab and refine your design and to find what's wrong with it, or you passed and you don't need to do anything else.